All right, we've reached the final step, step 5, in the process for designing a pumped safe water system. Again, my name is Jordan Deshawn, happy to be presenting this today. And the main question we're trying to answer here is what solar array design is needed to supply the power required by the pump, which was determined in step 4. And the first sub-step is 5A, where we'll be looking at the solar panels and the project conditions. So we define here the brand and model of solar panels that we'll be using, and then enter the solar panel specifications at standard test conditions in these cells. Then we'd also define things about our project location, such as the coordinates, the slope that will be used for the solar panels, the azimuth, which is the direction the solar panels will face, the design month, and why we would choose that as the month. In most cases, we want to choose the worst month with the lowest irradiance, or the lowest irradiance month. And then we'll enter irradiance and temperature data, which we get usually from PVGIS. So you may be wondering what that is, and this references tab is a great place to look. So PVGIS is a global solar database, and we can click this link to navigate to its website. So once there, you'll either be brought directly to the interface, or if you need to, you can click this button to get to the tool. And from this page, you can access irradiance and temperature data from anywhere in the world. So depending on where your project is located, you could select a point or enter the latitude and longitude coordinates and click Go. For this example, we'll just pick a random point and then define our slope here. In this case, we're in the southern hemisphere, so we're going to be wanting to point north most likely. And then we'll just visualize our results to see what the lowest irradiance month might be. In this case, it looks like it's either December or January. It looks like it's December. Next, we're going to click this Daily Data tab, select Local Time, and then define our worst month as December. We're interested in both irradiance and temperature, so we'll select those check boxes, define the slope as 15, and point them to the north, which is an azimuth of 180 on PVGIS. If you needed more information, you could click the azimuth button to read more. Then we'll click Visualize Results again to see the daily irradiance profile curve. And then you can click this CSV button to download the data. Very quickly, I'll go through, and again, if you need to pause and stop this video as I'm going through this so that you can follow along, feel free to do that. First, we're going to select all the entries in column A by clicking the A at the top, and then come to Data, and click this button, Text to Columns. And what this is going to do is going to parse so we can see it separately. Then we'll select the hours from 6 in the morning till 7 p.m. and we can copy that data and do the same for the temperature and paste that into our design pool. But we can see there's already data here from our example project, so we'll keep that there. The next step is to define the solar array configuration. So we're going to define the number of panels in series and the number of parallel strings. And then all of this is automatically calculated. It gives us the power output for a single solar panel and the power output of the solar array. Again, you'll need to experiment and do iterative design process to determine the proper number of panels in series and parallel strings. One of the main things we're looking for in defining the number of panels in series is to make sure our array VOC does not exceed the maximum limit for the inverter or the pump. And then when defining the number of parallel strings, we want to make sure that we're achieving high Pmax such that we get sufficient water production to meet our demand. And then there might be helpful calculators you can see in the Optional Calculators tab to estimate the number of panels in series or in number of parallel strings. And you can do that by entering this data for the solar array configuration table. Next, we're going to estimate water production, and the two main things to define here are the array efficiency and the inverter efficiency. And there's an optional calculator tab that could help you determine what the array efficiency is by entering the chosen loss percentage based on some references here. And then at the bottom, it gives us the total array efficiency. And finally, this automatically calculates our hourly water production. We see in this curve hourly water production and motor power, and that's based on where the system curve intersects the various pump curves at different operating frequencies based on the power input. And then all of that leads us to our design checks, where our goal is to determine if the daily water production is going to meet the design water demand. We can see here we get a percent difference, which is the difference between the daily water production and the design water demand. And in general, the water production should be within -5% to +20% of the design water demand. And we're here within -5%, which means it's probably a good design. If you needed to, you could go back and adjust the number of panels in series or parallel strings, or maybe even adjust the type of solar panels you're using. So the last thing we get is a summary of the number of panels in series, number of parallel strings, and then the size of the solar array in kilowatts, and lastly, the total daily water production. So that's the end of step 5 and the end of all of the steps of designing a pumped safe water system. I hope you enjoyed watching these videos, and as always, if you've got questions or want to learn more, please feel free to reach out to us. You can reach out to me personally. Again, my name's Jordan Deshawn, and I'm on the Charleston engineering team at Water Mission. But any of us on the engineering team would be happy to assist you. Thanks for watching.